All right, we are going to look at the first section in chapter 5. So chapter 5 is all about linear functions. We're going to be looking at different forms of linear functions, meaning like slope-intercept form, point-slope form. We're going to be defining slope. We're going to be looking at parallel and perpendicular lines, but we're going to be doing a whole bunch of graphing. So I hope you're ready to do some graphing. However, before we start that, we're going to start by defining what a function actually is and defining what domain and range of a function is. So we have two learning objectives for this section. Like I said, determine whether a relation is a function. We'll also be describing domain and range of a function. So let's start there. Let's start by defining a relation. A relation is a pretty broad definition, all right? We just say it's a pairing between two sets of numbers. And we can create a relation between really any two sets of numbers. If you look at the example in the book, they're relating age with height, okay? We could relate eye with your algebra grade, eye color with your algebra grade. We can relate really any two sets of information that we want to. But what's more important is whether or not our relation is what we call a function. This is a very important definition that you're going to want to memorize and know what I mean when I say function. So a function is a relation where, and here's the very important part, every input has exactly one output. Every input has exactly one output. And what we're going to be doing a lot in this chapter is writing a rule to relate the inputs to the outputs. So it's very important that we have those pieces or those definitions in our mind. Now, let's talk about inputs and outputs. A couple more important definitions for you to know. We like to use what's called the domain. What the domain is that's your inputs, okay? Now, typically, this is our x values. We might be using a function that uses other variables, but typically we use x and y, so your inputs would be your x values. And then your range would be your outputs, which are typically going to be your y values. Now, we sometimes say that the domain is the independent variable, and the range is the dependent variable. And the reason we call it, though, we say that is because the y value depends on what x value we pick. Where the x value, we can pick any one that's independent of what the other one says. So since the y value is dependent on the x value, we call it the dependent variable. And since we get to pick whatever x value we want, we call that the independent variable. And here's what we're going to do with that. If you look at your homework, it gives us a relation, and it tells us to list out the domain, list out the range, and tell if it is a function. So I'm going to start by just doing the example you can find in the book, example 1. They give us the following relation: 3, 4, 3, 6, 5, 14, and 7, 14. Let's start by listing out the domain values. And I like to list them vertically. You'll see why in a second. So my domain values, again, are all the x values. So I'm going to list those out. And you need to be very careful here because you notice my first two domain values are both 3. I only list 3 once. We do not repeat domain values. Then we have 5, and then we have 7. Then we want to list out our range values. Those are all of our y values. So we go ahead and list those out. We have 4, we have 6, and we have 14. And then we have 14 again, but again, we do not list it twice. Now here's the most important part. After we list out the domain, after we list out the range, now we want to represent the pairing of the two. So since we have 3 paired with 4, I draw a line from 3 to 4. Since we have 3 paired with 6, I draw a line from 3 to 6. Since we have 5 paired with 14, I draw a line from 5 to 14. Since we have 7 paired with 14, I draw a line from 7 to 14. Now the question remains, is this a function? Well, like we said before, a function is a case where every input has exactly one output. And if you look really close here, the input of 3 has 2 arrows coming off of it. Therefore, it has 2 outputs. The first output it has is 4. The second output it has is 6. Since we have an input that has more than one output, we say that this is not a function. All right. Looking at another example from the book. Let's do another one here. So this time they give me the relation 412, 518, 712, and 819. All right, and we want to determine if this is a function. So first I'm going to list out my domain values, which again are all of my x values. So in this case, we have 4, 5, 7, and 8. Then I want to list out all of my range values, which in this case we have 12, 18, 12, and 19. Again, do not list 12 twice. We only list domain and range values once. And then let's draw our arrows. So 4 is paired with 12, arrow from 4 to 12. 5 is paired with 18. Arrow from 5 to 18, 7 is paired with 12, arrow from 7 to 12, and 8 is paired with 19, looking like this. So the question is this a function? Well, the definition of a function says every input has exactly one output. If you look, each one of our inputs has exactly one output. It's okay that we have this situation here. You'll notice 2 arrows are going to the same output. That's fine. It's all about how many arrows are coming off of each input. So this one is a function. All right. Then the last thing I want to show will be from example 2 in the book. They give us a function. In this case, they give us 2x plus y equals 9. And then they give us an ordered pair, but the problem with the ordered pair is it's incomplete. They tell me that x is 1, they don't tell me what y is. Well, we can fix this. Here's what we're going to do. In our function, we are going to plug in what we know. So in this case, we know what x is, but we don't know what y is. So here's what we're going to do. We are going to plug in what we do know. I know that x is 1, and then we are going to solve for what we don't know. Okay, so what I did here, so I plugged in the fact that x is 1, and what we're going to do is we're going to solve for y. So 2 times 1 is 2, and then to solve for y, we want to get y alone on the left side of the equation. So since since we're adding 2 to y, we do the opposite. We subtract 2 from y. Of course, we do it to both sides of the equation, leaving us with y equals 7. So when x is 1, y equals 7. Okay? You may also be given a problem where they don't tell you x, but that they tell you y is 9. So you'd want to do the same thing here. Plug in what you know, solve for what you don't know. So 2x plus, in this case, I know that y is 9. So that leaves me with 2x plus 9 equals 9. I want to get x alone, so I'm going to subtract the 9 from both sides, leaving me with 2x equals 0. And then to get x alone here, I divide both sides by 2, leaving me with x equals 0. So what this tells me is when y is 9, x is 0. All right? So plug in what you know, solve for what you don't know. That should get you through your homework on section 5.1. Please email me if you have any questions.